Okay, we are on lesson 6.3. The S 4.3 means this is from another textbook that we are using. S stands for Spokowski, so that's how we differentiate between the other book and our current notebook, our textbook, sorry. 6.3 is using summation notation to talk about the area under the curve. Now, last lesson, we were using RM, LRM, MRAM to estimate the area under the curve. And you can see that because they're all the same width, we were able to factor out the width or the same base, right? The rectangles all have the same base. We're able to factor out the base and then add up all of the heights up to a certain point. Some of them for LRAM, we didn't use the last Y value. For RM, we didn't use the first Y value. So is there a quicker way of doing this? Some of you may know the summation notation, some of you don't. So I'm going to assume that we don't and go ahead and kind of start from there, right? Summation notation is just a very, very quick way of saying, here's a function, add up everything that after you plug it into the function, you have the Y values. Take all the Y values in and then add them up. Summation means, the sigma means to add up the values, right? So typically what you see in the summation is you have the summation, you have a f of x here, you have an equation there, and it tells you k equals 1, meaning your t table starts at 1. And the beautiful thing about summation is that your t table is always going to go by whole numbers. So your t table is going to go 1, 2, 3, 4, 5, 6, all the way to infinity, right? And they don't actually do any negatives. If you do have negatives, then there's other ways of working around that. But the formula itself, originally when it's intended, goes k equals 1 to a number that you stop up here. So for example, if I say, hey, I have the function, I say sigma of 2x plus 1, k equals 1, 4. That means over here I make a t table of 1, 2, 3, 4, and I plug all those numbers into my function here. So 2 times 1 is 2, plus 1 is 3, and then you get 4 plus 1 is 5, 6 plus 1 is 7, 8 plus 1 is 9. And then what the sigma tells me to do is take all these Y values and add them up. So my final answer to this summation problem will be 24. So why is that helpful? Well, in our rectangles, when we're doing our LRAM and RM, what we're doing is we're basically adding up all the Y values, right? So we were able to take our base and we add up all our height, our Y values. But if you recall in our notes, I keep saying f of x values, right? F of x values because those are your Y values. So it's just the f of x, it's the function, right? So then if we were to plug in, if we were to say sigma, k equals 1, and then however many rectangles we're going to make, we're taking these values and plugging it in so we get all the different heights of our rectangle and then add them all up and then multiply by the base, we will get the area under the curve. So summation notation is just a very quick way of saying exactly what we were saying before, but now with a little bit more flair, right? So a little bit more. Now, we're going to ignore that for now. I know this is kind of weird, but let's go ahead and look at what it's trying to say. So it says that AB, ignore the 5 and 6. This notice was revamped, so then the numbers got a little bit mixed up. So this is number 1, right? It says let A be the area under the curve of the given function f from A to B. So A is 0, B is 2, right? A is 0, B is 2, right? Approximate the area by dividing A, B into sub-intervals of equal length delta x and using AIP and ACP. What does IP mean? IP is inscribed partition, meaning every single rectangle needs to be inscribed, needs to be under. If you look at the previous notes, the last problem, we talked about inscribed and circumscribed, and that's this one. CP is circumscribed. Partition. You could kind of interpret this as LRAM and RM, but it's a little bit different than LRAM and RM because this one, we want all my rectangles to be completely under and all my rectangles to be completely over so that when you kind of average the two of them, you get a nice estimate of it, right? When you have LRAM and RM, depending on the way the curve goes, sometimes within one function, within one area, you have over and under. So this is very specific. We only want under and we only want over, right? And so if you were to look at this the way we did in the previous 2 lessons, what this is really asking for is it's looking for the area under the curve, right, for your dx from 0 to 2, that's your A and B. right? And then it wants delta x to be 1/2. So this time, instead of telling you I want how many rectangles, I am telling you that each rectangle has a width of 1/2. Meaning when I make my t-table over here, which are already provided for you, you can go ahead and go up 1/2. So 1/2, 1, 3/2, 2. And the reason why I'm going with fractions now is because now plugging that into my function, it's going to be a little bit easier to calculate the numbers, right? So 4 minus 0 squared is going to be 4. 4 minus 1/2 squared is 1/4. So 4 minus 1/4 is 15/4. 4 minus 1 squared is 3. 4 minus 3/2 squared, that's 9/4. So that gives me 7/4. Checking here. 4 minus 4 is 0. Okay. Now, with these functions, you really want to make sure you check the graph, and that's why we graph it out, right? Well, I provide the graph for you. You have to look at the graph and say, okay, in order for me to totally circumscribe this function, or actually in order for me to be complete inscribed, because part A says inscribed, right? So we're going to be inscribed first. In order for me to completely inscribe, I need to not do LRAM for this one. I need to do RRAM, because then I can be totally under the curve like so. So this is my RRAM, right? So for part A, for an area that's completely inscribed, it is going to be a width of 1/2. And this is RRAM, so I'm not using the first Y value. I'm going to add up all, oops, not the first one, sorry. Add up all the rest of them, 15/4 plus 3 plus 7/4 plus 0. I know the 0 is very unnecessary, but I'm trying to show you that I used all the Y values except the first one, right? So that's 1/2. That's going to be 22/4 plus 12/4. That will give me 34/8. 17/4 is my complete inscribed area, right? Now I'm going to look for circumscribe. So circumscribe in this case, I'm going to use LRAM, because if I use LRAM, I can see I go from the left side over, I'm going to be over the graph completely in every step. So it's going to be an overestimate that way, right? So part B, for a circumscribed partition, 1/2, I'm using LRAM, so 4 plus 15/4 plus 3 plus 7/4. That gives me 1/2. That is 7 plus 22/4. 1/2. 28 plus 22/4. That gives me 50/8. 25/4 is my circumscribed partition estimate. Okay, and of course, again, you kind of divide, add them up, find the average. That would be a really good estimate of that curve, that area under the curve. Okay, so keep in mind the width of your rectangles here, right? We talked about this and we use the word base, but let's just kind of try to remind ourselves what happened here. So what happened here is when we add up all the rectangles, we used our base, which is B minus A over N, right? That's how wide it is, and that's the 1/2. And even though they gave it to me, I could still kind of figure that out. This is 4 rectangles, so 2 minus 0 divided by 4 gives me 1/2. That's how wide each of my rectangle is. Then my height was all the Y values, right? But Y values, by plugging in various X values. And how do we know what the X value is? Well, the X value was really each of the bases, right? Each of the bases. So, and then kind of increments of that. So I had B minus A over N, I had a 1/2. So we started, depending on which one we were using. If we started with this one, we started with 1/2. So we started by plugging in 1/2, and then I plugged in 1, and I plugged in 3/2, I plug in 2. So I can say that's N equals 1 times 1/2. N equals 2 times 1/2, N equals 3 times 1/2. Notice that's giving me all the different values I need. N equals 4 times 1/2, right? So the N is helping me move along the x-axis, move along the t-table to get the next y value, to get the next y value. The exact x value I'm plugging in, that comes from my width, my base, right? So depending on my base, I know how to move on to the next number, okay? So keep that in mind, because then the next one tells me something else, right? So now, It says find the area of the graph of the given function from 0 to b. So in this case, I'm 0 to 2 again. It's not always 2, but it just so happened we're using 2, right? And we're going to use inscribed rectangles and circumscribed rectangles. The function itself is 4x plus x cubed. You always want to graph it out because you want to see the curve of the graph. We'll talk about the curve of the graph a little bit, right? And then it says I want to get up to 2. So in terms of what I'm looking for this area. This is the area I'm looking for, okay? But it doesn't tell you how wide to make the rectangle. In fact, I don't know how many rectangles I have. Actually, I do. I have infinity rectangles, right? Think about what we're saying here. If I have 2 rectangles here, my estimate is going to be either over or under, completely under. That's not very good. Okay, totally agree. How about 4 rectangles? Is 4 rectangles better? So 4 rectangles a little bit better, but I still have a lot of overage, right? 4 rectangles. What about, instead of having 4 or 2, what about if I have, let's say 20? So if I cut this up to 20 rectangles, right? And then I can see my little overage. Do you see how now my overage is so much smaller than before? So can you imagine fitting infinity rectangles in there? Are we going to get a very, very, very good estimate? In fact, the overage is going to be so minuscule that you can actually overlook it and say we are actually finding the area under the curve to the exact number, right? So how does that happen? Well, we use algebra, not calculus, it's algebra. It's very cool. All right. So remember, the width is the base. We were talking about this. The base is b minus a over n. Well, b is 2. A is 0 because it started at 0. So that's why this base is 2 minus 0 over n. N is infinity. All right, keep in mind n is infinity because we have infinity number of rectangles here. Okay. All right. So the inscribed rectangle in this shape, if I zoom in, inscribed rectangle will start with L round here because it starts here on the left-hand side, left-hand side, left-hand side, left-hand side, left-hand side, left-hand side, right? So all my inscribed rectangle is going to start on the left end. I'm going to start at 0, right? I'm going to start at 0. Now, remember, summation cannot start at 0. Summation starts at k equals 1. All these formulas up here starts at k equals 1. So I need to force it to be 0, so I started at k minus 1. Remember, this is how the n equals 1, n equals 2 times my base. So this is really k minus 1, that's my n equals 1, because that's 0, times my base of 2 over n. Okay. If I want circumscribe actually is going to start at the L round. So circumscribe is going to start here, start at the next number. Well, 1 over will actually start us at k. So this is really k, because it starts at k equals 1, and then it's going to multiply by 2 over n. Okay, so it is important to know where we start, and we'll talk about this a little bit more once we start going with the formula here, but you need to do both. You'll need to do the inscribed and the circumscribed, right? So what does this look like? Well, get ready for algebra, okay? All right, so what are we doing? We're adding up infinitely many of these rectangles, base times height. So we are adding part A, we're adding up A equals 1, adding up to infinity rectangles of base times the height times the function, plugging in these numbers all the time. What is my function? My function is 4x plus x cubed. So 4x, that's my x, plus x cubed. All right. So again, you need to know how to set this up, because this is the way we figure out all the y values, all the height of each of the rectangle that I'm dealing with. And then I put it into this formula so I can figure out what the summation is at the very end. All right. So the hardest part is figuring out the k minus 1. Which one is the k minus 1? Which one is the k? And then you multiply it by the width, because that will move you along on the t-table to the next value. And what t-table am I talking about? It's the function I'm dealing with. So it's the f of x given to you in the problem. Okay. All right. So summation is just algebra. What we're going to do next, right now, our task is to clean this up, because the goal is to use some of these summation formulas to help me out, right? It says that if you have this k, the formula is this. If you have k squared, the formula is this. If you have k cubed, the formula is this, right? And if you have a constant, the formula is this. These are basically the 4 formulas we're going to be using in this chapter, in this unit, all right? All right, so let's not get away, not get carried away. Let's go ahead and work this out. What we want to do right now is there's way too many parentheses, right? So let's go ahead and clean this up, multiply all this out, distribute, and see if we can get this to be a little bit cleaner, okay? All right, don't forget your sigma. The 2 over n is outside. I'm going to deal with the inside first. So 4 times 2 times k minus 1, that gives me 8k minus 8 all over n. Okay, this one's a little bit trickier. You have 2 times k minus 1 and then cube. So 2k, essentially you have 2k minus 2 cubed. So I'm going to use my Pascal's triangle here to kind of help me out. It's 1, 3, 3, 1, and that's 2k cubed, 2k squared, 2k, and then negative 2 cubed, negative 2 squared, negative 2 to the 1, all right? So that will give me 8k cubed minus 2 times 3, that's 6 times 4, 24k squared, okay? And then 2 squared times 2 is 8, times 3 is 24 again, so plus 24k, and then minus 8 all over n cubed. Remember, the whole thing is being cubed, right? Okay, all right, so now what you want to do is you want to go ahead and split these up into individual fractions. Kind of weird, I know our usual case is 1 fraction, but in here you actually want multiple fractions. So I'm going to do 2 things at the same time. I'm going to split this into 2 fractions, 8k over n minus 8 over n. Also distribute the 2 over n to every single term, okay? So let's go ahead and see how that goes. So you have sigma k equals 1, n. The first term will give me 16k over n squared minus 16 over n squared, right? I go ahead and distribute that out, plus 16k cubed over n to the 4th minus 48k squared over n to the 4th plus 48k over n to the 4th, sorry, minus 16 over n to the 4th. All right, so every single one is on its own. Okay, so keep in mind, n is infinity, right? N is a number. K is the variable that we're dealing with because you're plugging in k equals 1, k equals 2, k equals 3. So what you can do now is you can split each of these terms up into its own individual sigmas. I know it sounds like a lot, but trust me, be patient, it will work out, right? So the first one you want to go ahead and split up, and you want to take out whatever is not k to be your coefficient to go in the front. So the first term becomes 16 over n squared, sigma k equals 1 n k, minus 16 over n squared, sigma k equals 1 n 1. There's a 1 there. You don't want to say 0. So I'm on this term here, okay? Then plus 16 over n to the 4th, sigma k equals 1 n to the k cubed, minus 48 over n to the 4th, sigma k equals 1 to the n, k squared, 48 over n to the 4th, sigma k equals 1 n to k, minus 16 over n to the 4th, sigma k equals 1 n to the times 1. Okay, all right. So what is the point of all this? Remember, we have these formulas up here, right? The k, all the sigma of k of k equals 1 to the n can be replaced by this n times n plus 1 over 2, replaced by this formula, all right? And then the k squared can be replaced by this formula, k cubed replaced by this formula, okay? All right, so the first one, I have 16 over n squared. This got replaced by n times n plus 1 over 2, right? That was the formula there, okay? Minus 16 over n squared. And when it's a constant, you gotta move up, It is simply n times c, right? So n times c. So that becomes n times c, n times 1 is n, okay? And then your next one, 16 over n to the 4th. This one is the k cubed formula. The k cubed formula is awesome. It is n times n plus 1 times 2n plus 1 all over 6, okay? Minus 48 over n to the 4th, k squared. K squared is, I believe, oh, oops, wrong one. That's the one. That one's k squared. Okay. So what happens when I didn't scroll up? Okay, so k cubed is actually n times n plus 1 over 6, the whole thing squared. Okay, and then minus 48 over n to the fourth. Yeah, k squared is the one that's a little bit longer. It is the n times n plus 1 times 2n plus 1 all over 6. Okay, and then plus 48 over n to the fourth. K is n times n plus 1 over 2 minus 16 over n to the fourth times 1 again, and that's a constant, so n times c, n times 1 is n. Okay, all right. So again, this is all algebra. This is, I'm not doing much calculus here, okay? All right, we're gonna have to multiply these out and clean up because I got a bunch of n's everywhere, right? Okay, so first things first, 2 goes into 8, 2 goes into 16 8 times, and then you have n squared. So in this step, I wouldn't recommend you to do too much because it gets too messy, right? So I would go ahead and just multiply that out and go 8n squared plus 8 all over n squared. That came from that term, right? Minus 16n, and n reduces out, 16 over n. That looks pretty good. Plus, okay, so this one's a little bit trickier. You have, oh, I messed up here. This is a 2. Apologies. All right, so 2 down here. Okay, so now I'm reducing this. 2 squared is 4. 4 goes into 16 4 times. So 4, and then you have n times n plus 1 squared. So that's n squared plus n squared. That gives me n to the fourth plus 2n cubed plus n squared all over n to the fourth. Right, you have to know a bunch of your algebra skills to make sure you got everything down, okay? And then you have the next one, 6 goes into, oops, sorry, that ran away. And then 6 goes into 48 8 times, and multiply all this out. N times n plus 1 times 2n plus 1. So if you distribute the first one, you get n squared plus n times 2n plus 1. That gives me 2n cubed plus 2n squared plus n squared plus n. So that's 2n cubed plus 3n, sorry, plus 3n squared plus n all over n to the fourth. Now there's quite a bit of extra math you have to do on the side, okay? And then 2 goes into 48, 24 times n squared plus n. Oh, this one's nice. I can just go ahead and distribute. So I can go n squared plus 24n all over n to the fourth. And then the last one, 16 over n cubed. Okay? All right. So then let's go ahead and, again, you want them to be individual fractions. So it's kind of, again, counterintuitive to what we are used to, but it will work out, I promise. Okay? All right, so keep forgetting my equal because this is just the next row. Okay, so now you have 8n squared over n squared. That's 8 plus 8 over n squared. This one's still 16 over n. That doesn't do much. Plus 4n to the fourth over n to the fourth. That's 4. Plus 2 over n. Plus n squared over n to the fourth. 1 over n squared. Minus 16 over n, because n cubed over n to the fourth, minus, I'm distributing the minus, 24 over n squared, minus 8 over n cubed, plus 24 over n squared, plus 24 over n cubed, plus 16 over n cubed. Okay, so keep in mind, how much is n? N is infinity. So now we go all the way back to our very first calculus lesson, which is limits, right? So limit as n approaches infinity, because we can never reach infinity, but we know we're approaching it, right? Of all of this, right? All this, you don't need to rewrite the whole thing down. What is going to happen? When you're dividing 8 by infinity squared, you're essentially reaching 0. Anything divided by infinity is reaching 0. All of these with infinity, whether they're squared or not, is reaching 0. So you're left with 8 plus 4. Your area is 12. Are you always going to get a clean answer like that? No. But are you always going to get an answer without an n? Absolutely. So your answer should not include an n. Your answer should be a nice, clean, real number. Okay? All right. So now what do we need to do? Not only do we need to do it for, this is our inscribed partition, we now need to do the circumscribed partition, because you'll see for some reason, magic's going to happen. All right. So now we're going to do circumscribed partition. Let's use a slightly different color so you can see. All right. So for my circumscribed partition, we start at k equals 1. So we start at k. So what I'm plugging in is a little bit easier. It's 2k over n. So my width is still the same, 2 over n. I'm still plugging into the same formula, 4x plus x cubed. So 4 times 2k over n plus 2k over n cubed. Okay. All right, we're going to do the same exact thing. We're going to have to clean this up a little bit. So sigma k equals 1 to the n, 2 over n first. Well, actually, I think I can distribute this out. This is a lot quicker to distribute. So if I distribute the 2 and multiply it to everybody, 2 times 4 is 8. 8 times 2 is 16. 16k over n squared plus 2k cubed. So that's 8k cubed times 2, 16k cubed over n cubed. All right. So for these problems, one of the ways, whether inscribed or circumscribed, is going to be a little bit shorter than the other, because without the k minus 1, your algebra is a lot less than before. Okay. All right. So this time I have 2 sigmas I can split up. So, oops, my sigma looks funny. K equals 1, k plus 16 over n cubed. Remember, we're pulling out my constants. And now I'm using the formula. K is n times n plus 1 over 2. And then 16 over n cubed. K cubed is the one that was n times n plus 1 squared. Okay, so your parentheses have to be in the right places, otherwise you run into trouble like me. Okay, all right, so now let's clean this up. Okay, I have 2 go into 16 8 times, 8n squared plus 8n all over n squared, plus, remember, 2 squared goes into 16 4 times n times n plus 1 squared. That's n squared plus n squared. That's n to the 4 plus 2n cubed plus n squared all over n cubed. Right? So now, hold on a second. I think I'm missing something. What did I miss? Give me a moment here. 16k. Oh, whoopsies, my fault. This is why this is dangerous. I forgot that there's one more n down here because I had n cubed times the n here, so that's n to the 4th. So minor mistake, but that makes a huge difference in my answer. That's why I'm going, that's not looking right. Okay, sorry about that, but good catch. All right, now split them into individual fractions. So you have 8n squared over n squared, which is 8, plus 8n over n squared is 8 over n, plus 4n to the 4th over n to the 4th is 4, and then 8 over n, and then 4 over n squared. So same as before, at this point now you can say limit as n approaches infinity of this whole thing, and you don't have to rewrite everything because it's such a pain, but all the ones with the n on the denominator will go to 0, and hence you get the same answer. This is what I'm talking about magic, 12. So again, when you have infinitely many rectangles, you will see that it really doesn't matter whether you're inscribed or circumscribed. Your answer is going to be the same. However, don't be lazy on your tests and quizzes. You have to show me both ways, all right? So a few tricks to help you remember what to do in these cases, right? So if your graph is going to start at 0, if your y value is going to start at 0, so if your f of x value starts at 0, you're going to use a minus 1, okay? If your f of x value starts next to 0, it's the next number over, but it's not necessarily 1. because of your width, right? But that's not the point. The point is if it's not 0, you're going to use k. Okay. Now, when is it going to start at 0? When is it not? Okay. So you have 4 different types of graph. You have a concaving up, decreasing, concaving up, increasing, concaving down, increasing, concaving down, decreasing. In these graphs, we're usually starting at 0 and on. So you're usually starting at the axes. So your graph's gonna look something like this or like this, right? You're gonna start at the edge. So don't worry too much about what you're going to, there's not a lot of tricks on these, right? So with this one, with the first graph, you can see my very first inscribed, right? Inscribed, I have to be inside. So my inscribed is gonna start at k, but my circumscribed is gonna start at k minus 1, right? So circumscribed, I'm gonna shorthand this. So CP is gonna be k minus 1. IP is gonna be k. All right, this one, same thing. If you want to be inscribed, you're gonna start at k. You're gonna start at k minus 1. So for this one, your inscribed is gonna be k minus 1. Your circumscribed is gonna start next one over. It's gonna be on top, right? So circumscribed is gonna be k. This one, your first one's gonna be inscribed, so it's gonna be under. So inscribed is gonna be k minus 1. And your circumscribed is going to be over here. You're going to start the next one. So your circumscribed is going to be k. So these two are exactly the same. So they're both increasing. Any graph that's increasing is going to start at k minus 1 for inscribed, and it's going to start at k for circumscribed. Whereas if it's decreasing, you're going to start at k minus 1 for your circumscribed. And then the next one over be your inscribed. Okay. So hopefully this will help you, because the formula, really the summation formula, is going to be the width, right, times f of width times either k or k minus 1. That's your function. And then k equals 1 to the n. This is the basic form of every single problem. Once you have that down, this is not going to be that bad. Okay. All right. Make sure you do all the homework for this section. It is very important that you get adequate practice. Okay. That's it.